All right, and so in this little pencast, we're going to talk a little bit more about the Doppler effect. I'll show you some demos in class if I haven't done so already, but this says when a source of sound waves and a listener, so the source is something that's producing sound, and the listener, that's you, the observer. I'll go ahead and write that. I like that. Listener is the observer. Okay, so if you want to write that down, when the source of sound waves and the observer or the listener approach one another, the pitch of the sound is increased as compared to the frequency heard if both of them were just sitting there at rest. If the source and the listener, once again the observer, recede from one another, the pitch will decrease. This phenomenon is known as what we call the Doppler effect or Doppler shift. Common examples of the Doppler effect include the change in pitch of a siren of a police car or an ambulance as it passes at a high speed, as well as a change in pitch of a whistle of a passing train. A general statement regarding the Doppler effect can be made as follows. The Doppler effect will occur whenever there is relative motion between a sound source and an observer. If the source and the observer move closer, the perceived frequency of the sound by the observer will be higher than the sound's actual frequency. The opposite is true if they move further apart. Let's go ahead and highlight this. This is pretty good. The Doppler effect will occur whenever there's relative motion between a sound source and an observer. Now, these two things, I would highlight or underline this. This is important. If the relative motion is that they're getting closer, the observer is going to perceive a higher frequency than what actually is happening. And then if the relative motion is that they're getting further apart, then the perceived frequency will go down. All right, so what we're going to do is we're going to quantify a couple of these things. Don't worry about the little squiggly lines, but we're going to quantify a couple of these by this. So V sub sound is going to be the speed of sound. Now, in air, that could change, but remember, speed of sound in air is velocity equals 331 plus 0.6 Tc. Okay, F is the actual frequency of the sound. So, like if it's not moving, just the frequency, the output frequency. Output frequency. So the speaker is moving back and forth at a certain frequency. So, or whatever's producing the sound is producing that frequency, and so that doesn't change. I mean, that's just doing what it's doing. V source is the speed of the moving source. So like if something like the police car, or if like you literally had a speaker on a cart and you push the cart, that would be the speed of the source. V of the observer would be the person who's observing it. All right, and then F prime is what we call the perceived frequency of the observer, the perceived frequency. So F is going to be the frequency of sound. F prime is going to be the perceived frequency of the sound by the observer. So let's take a look. This is on page 11-13. So let's go on the next page. So 11-14. You have this picture right here. Now, if the source wasn't moving at all, it would be right here in the middle, and it's producing these wave fronts. Okay, and imagine this. This looks kind of like a ripple effect in a pond, but imagine these are spheres. So like the source is emitting a spherical wavefront, and the distance from this, so like this might be a peak, and this would be a peak. The distance between them is the wavelength. So let me zoom in actually. Okay, so this from here to here would be the wavelength. Okay, from here to here is another wavelength. From here to here is another wavelength. So the distance in between successive wavefronts is the wavelength. And remember, velocity is equal to frequency times the wavelength. That is constant for once it's in air. All right, so if I emit a higher frequency, the wavelength will go, if a higher frequency means wavelength will go down. All right, now if you take a look at this, this is an example of something moving to the left, and it'll emit a sound, and then it moves a little bit left and emits another sound. So what you're actually happening, the phenomenon is whichever way the source is moving, it's kind of like these wavefronts are closer together, and then behind it, they're further apart. So this is what we would say, this is the perceived wavelength there, and then this is the perceived wavelength, and I'm going to put a little prime. That is the perceived wavelength. So let me make this even bigger. I'll erase that. So if you're behind the source and it's moving away from you, you're going to get these wavefronts less often, which means that your perceived frequency is less than the actual frequency. All right, on the front side of this, the wavelength prime is smaller, so your perceived frequency is going to be greater than the actual frequency of the source. This guy is still emitting the same frequency, but depending upon which way he's moving and where you are, maybe if you're over here, there's you, you're going to perceive a higher frequency than what it is because these wavefronts are hitting you at a faster rate. This should make sense, right? He emits a sound, it moves in a sphere around it, then he moves a little closer, and then the next sound. So take a look. When he emitted this sound, he was right there. When he emitted this wavefront, he was right in the middle, so right there. And then when he emitted this one, he's like right in the middle of all of that. So do you see he's moving to the left? So here's where he first emitted the first wavefront. This is the second one. This is the third, and this is where he is for here, this fourth wavefront that's right there. The perceived frequency when you're there is higher than the actual frequency of the source. And then when you're behind, let me erase that. When you're behind right here, there you are, then the perceived frequency is less than what the actual frequency is. And so I'm going to derive an expression for you guys dealing with all this, okay? So what I'm going to do is I'm going to draw a stationary source, all right? So this is stationary at first, okay? And so what you're going to do is you're going to have basically a dot, and he'll emit a sound. And so here's the wavefront at some time t. Now, if we call that time the period, right, he's oscillating back and forth and emitting these wavefronts, then some time later, this one will go to that one, and then he'll emit this other one. So this is the wavelength right there, from there to there. And then the time for that to do that is the period. Okay? So we know that right now that the time for that to do that is the period. Okay? And so we know that frequency is equal to the velocity over wavelength. That comes from the fact that velocity is equal to frequency times wavelength. Okay? And then we could say that the period, which we know is 1 over the frequency, is equal to the inverse of that. So that would be lambda all over v. Okay, so I can rewrite that as that. And this would be v of the sound. So I'll just write v sound. All right, so there's the wavelength, the speed of sound in air, and then this is my period. Okay, so then that's when he's stationary. Now let's say he moves to this location right there. Okay, so I'm going to do this in red so you can see this. He moves to this location. Okay, so he emits the sound, the first sound when he's right here. Okay, and it's going to get to that spot. Then he moves here and he emits the next sound. Okay, so if he would have stayed still, this red one is this guy right here. Do you guys see that? If he would have stayed at that spot, but he moved to the right. Okay, he moved to the right some distance. I'll call that d. So this little distance, I'll do this in blue. That distance, I'm going to call that d. Okay, and that's the distance that the source moves. So I'll go ahead and write distance of the source. So this guy, let's say he's got some velocity to the right. Okay, so take a look. If he would have stayed stationary, this is where the second wave that he would have sent out. But he moved a little bit to the right. Okay, he moved a little bit to the right, and then when he emitted the next one, he actually got a little closer. Okay, now this original wavelength is what would have happened if he stayed still. The new wavelength is this distance from here to here. That's the new wavelength from there to there. So I'm going to call that wavelength prime. That's the new one. That's what we would consider the perceived wavelength. So these wavefronts on the front side, on this side over here, are getting closer together because he emits that sound. Now, the distance he moves in between each source, okay, we know that velocity is distance over time. So distance is velocity times time. So that is the distance that the distance the source moves is the velocity of the source times the time it takes for him to move it. But it's the time that he emits the next sound. And so what's the time it takes for him to emit the next sound? That's just the period. That's capital T. Okay? And so what I'm going to do now, so we know all that stuff. So let's go back to this picture here. I'm going to call the distance, when it was standing still, the distance between successive wave peaks, I'm just going to call that d. That's the distance it travels. That just happens to be the wavelength. Okay, so that's the distance. Now, wavelength prime, okay, wavelength prime is the distance, okay, so take a look. This distance right here is d. The distance is d, right? That distance. Then this guy moved d source. He moved that distance there. All right, and so where he emitted this is wavelength prime, this little separation here. Okay? If you see that, wavelength prime equals the original distance minus the distance that the source moved. Okay, so this was my original wavelength there. That's the distance, the original distance that we were at, and then minus the distance the source moved. So he emits a sound. If he was standing still, the distance between each successive wave peak would just be d. But then he moves closer. So this is he's moving towards. Okay, so he's moving towards the right. This is a key idea right here. All right, so what's the distance right there? So what I'm going to do is I'm going to say, all right, wavelength prime is equal to the original wavelength minus the distance that the source moved, which is just v source all times the period. Okay, so we have that right there. Now, the period, if we go back up to here, is that right there, right? That's the period. The period is the wavelength, the actual wavelength, divided by the speed of which the sound is going to travel. So wavelength prime is going to equal the wavelength minus v source times the period, which is just wavelength all over v of the sound. So this is however fast it's traveling in whatever medium it's in this case, air. Okay, well, they both have wavelength in common, so I'm going to pull that out. So wavelength prime, this is the perceived wavelength. This is what you would feel if you were standing in the front. That is equal to wavelength times 1 minus the velocity of the source all over the velocity of the sound. Okay, and so what I can do now is that's a key idea. Let me box that in right there. That's a key idea. So the perceived wavelength is simply the wavelength minus v source of the v sound. So here's the thing. If the source and the sound, like let's say the source is not moving at all, right? That's just a stationary. That becomes zero. This whole thing becomes zero. And so the wavelength that you would perceive is the actual wavelength. Okay? If you're moving closer, if you're moving somewhat faster, then the wavelength that you're going to perceive is going to be smaller than the wavelength that is actually there. Okay? Now, we know that v is equal to f lambda, so the perceived frequency would be velocity, and this is the speed of sound in air, so the velocity of sound, all over the perceived wavelength. All right? So the perceived frequency that you would hear is the perceived wavelength, and then this is the medium that it's traveling in. Okay? This is constant right here. Okay, that's constant. And so what I'm going to do is I can say, all right, we know that wavelength prime is that. And so I'm going to plug that in right there. So I'm going to get that f prime is equal to v sound. By the way, v sound is simply the frequency times the original wavelength. That's how fast it's going to travel, right? The frequency times the wavelength. All over this term, 1 minus v source all over v sound. Okay, and so I'm going to plug that in. Let's go ahead and keep going. So f prime is equal to the original frequency times the original wavelength. Because remember, this is a constant. If that's a constant, then if I take the original frequency and the original wavelength, that's what I get. And I get and then 1 minus v source all over v sound. Oh, and I forgot to plug in the wavelength right there, so that should be right there, and that should be right there. And so I'm going to cancel those two things out. And so I get that the perceived frequency, this is for an observer who is still, and the source is approaching. Okay, so let's write that down. That is equal to f all over 1 minus v of the source divided by v of the sound, the speed of sound waves. And so that's what I get for my my formula for this particular case. Now, if the source is moving away, okay, so the observer's still, he's still, but source is moving away, then it's lambda prime, instead of being this lambda where it was d minus d source, it'll be d plus d source. And if you go back and look at all the derivations, what will end up happening is that this sign that's right here will become a positive. And so I'll get f prime is equal to F all over 1 plus V source all over V sound.